Hi there, and welcome. My name is Matthew Gray. I'm grateful you've arrived here tonight, because we're about to drift through something extraordinary. The planets above us aren't just distant worlds. They're part of an arrangement so precise, so quietly balanced, that it seems almost impossible. Wherever you are right now, whatever brought you here, this is your moment to let everything else fade away. Tonight, we're traveling outward, but staying grounded in wonder. We'll visit the 8 worlds that share our neighborhood, each one moving in perfect rhythm with forces older than memory. From Mercury's patient dance with the sun to Neptune's frozen winds that have blown for billions of years, every planet holds secrets that can calm your mind and shift how you see the sky. Some of these discoveries might surprise you. Others will simply wash over you like waves on a distant shore, gentle and endlessly soothing. What matters is that you're here, breathing slowly, ready to rest. If this journey brings you peace or sparks something curious inside you, consider liking and subscribing. It helps others find their way to this quiet place, one restful night at a time. But for now, settle in. Close your eyes if you'd like. Take a slow breath, and let's begin this peaceful drift through the silent architecture of our solar system. Mercury completes 3 rotations on its axis for every 2 orbits it makes around the Sun. This means that if you stood on its surface, you would see the sun rise, set, rise again, and set again, all during a single Mercurian day. The pattern repeats endlessly, a rhythm locked into place by gravity's gentle pull over billions of years. It's called a 3-to-2 spin-orbit resonance, and it happens because Mercury is so close to the Sun that tidal forces have gradually synchronized its motion. The same forces that cause ocean tides on Earth have sculpted Mercury's rotation into this perfect waltz. Imagine standing on grey plains of ancient rock, watching the sun trace slow arcs across the black sky, rising and falling in a pattern that never changes. There's something deeply calming about that kind of constancy. Mercury doesn't rush. It simply follows the path, carved by time and gravity, turning in a rhythm that will continue long after we're gone. And in that rhythm, there's a kind of peace, a reminder that some things in the universe move with perfect, unhurried precision. On Venus, the atmosphere is so thick that if you could stand on its surface, you wouldn't see sharp shadows. The light from the sun scatters through 93 times more air pressure than Earth, spreading into a soft, even glow. It's like being deep underwater, where light becomes diffused and gentle. The sky itself would appear a hazy orange, almost amber, with no single direction of brightness. Everything would be illuminated from all sides at once, wrapped in a luminous fog that never changes. Venus rotates so slowly that a single day lasts 243 Earth days, longer than its year. The sun moves across the sky at a pace so leisurely that you wouldn't notice its shift. Time itself seems to expand on Venus, stretching into something vast and unending. The clouds above, made of sulfuric acid droplets, reflect most of the sunlight back into space, which is why Venus shines so brilliantly in our night sky. But beneath those clouds, the light is muted, calm, and constant. There's no day and night in the way we know it, just a perpetual twilight that wraps the planet in stillness. Earth's moon is slowly drifting away from us at a rate of about 1.5 inches every year. The distance is so small that no one would notice it in a lifetime, but over millions of years, it adds up. 4 billion years ago, the moon was much closer, filling more of the sky and creating tides far stronger than the ones we see today. As it moves farther, Earth's rotation gradually slows, lengthening our days by tiny fractions of a second each century. The two bodies are locked in a dance governed by tidal forces, transferring energy back and forth in a process that will continue until the sun itself grows old. One day, billions of years from now, Earth will always show the same face to the moon, just as the moon already shows the same face to us. This process is called tidal locking, and it's the universe's way of settling motion into stillness. The moon's retreat is gentle, almost invisible, but it's a reminder that even the most constant things in our lives are part of a slow, quiet transformation. It's not something to fear, it's simply the way gravity shapes time. Mars has the tallest volcano in the entire solar system, a mountain called Olympus Mons. It rises about 13.5 miles above the surrounding plains, nearly 3 times the height of Mount Everest. But because Mars has lower gravity and no tectonic plates, the volcano grew slowly over millions of years without being pushed or shifted. Lava flowed from the same spot again and again, piling up in layers that spread outward in a gentle slope. The result is a shield volcano so wide that if you stood at its base, you wouldn't even realize you're on a mountain. The slope is so gradual that it would feel like walking on flat ground, rising only a few degrees with each step. The summit is hidden beyond the horizon, unreachable by sight. Olympus Mons is ancient now, quiet and dormant, covered in dust that has settled over eons. No eruptions disturb its slopes. No wind strong enough to reshape it blows anymore. It simply rests, a monument to forces that shaped Mars long ago and then fell silent. There's something profoundly peaceful about a mountain that no longer trembles, a peak that will stand undisturbed for billions more years. Jupiter's Great Red Spot is a storm larger than Earth, and it has been raging for at least 300 years, possibly much longer. Early astronomers observed it through their telescopes and sketched its oval shape, noting how it drifted through Jupiter's clouds but never disappeared. The storm rotates counterclockwise, spinning once every 6 days, driven by winds that reach speeds of 270 miles per hour. But despite its violence, the storm is also stable. It doesn't grow or shrink erratically. It doesn't move unpredictably. It simply turns, held in place by the flow of Jupiter's atmosphere, a pattern sustained by the planet's rapid rotation. Jupiter completes a full turn in less than 10 hours, the fastest spin of any planet. And that motion creates bands of wind that run parallel to the equator. The Great Red Spot sits between 2 of these bands, trapped in a groove where opposing currents hold it steady. Over centuries, it has shrunk slightly, but it continues to turn, a deep crimson swirl in a sea of pale orange and white. To watch it would be to see something timeless, a storm that exists not in chaos, but in balance. Saturn's rings are made of billions of chunks of ice, some as small as grains of sand, others as large as houses. They orbit the planet in perfect alignment, held in place by gravity and shepherded by tiny moons that clear gaps and keep the structure intact. The rings are remarkably thin, stretching hundreds of thousands of miles across, but measuring only about 30 feet thick in most places. If you could shrink them down and keep the proportions the same, they would be thinner than a sheet of paper. The ice reflects sunlight brilliantly, which is why Saturn appears so luminous through a telescope. But the rings are ancient, possibly as old as the solar system itself, or perhaps the remnants of a moon that wandered too close and was torn apart by tidal forces. No one is certain. What is certain is that they're temporary. Gravity is slowly pulling the rings inward, raining ice onto Saturn's atmosphere in a process that will erase them in another 100 million years. For now, though, they remain, glowing softly in the darkness, a reminder that even the most beautiful structures are just moments in the long flow of time. Uranus rotates on its side, tilted at an angle of 98 degrees compared to the plane of its orbit. This means that instead of spinning like a top, it rolls through space like a ball. For about 42 Earth years, one pole faces the sun, experiencing constant daylight, while the other pole remains in darkness. Then, as Uranus continues its 84-year orbit, the roles reverse. The dark pole gradually tilts toward the sun, and the bright pole drifts into shadow. Scientists believe this unusual tilt was caused by a collision with another massive object early in the solar system's history, an impact so powerful that it knocked Uranus onto its side. The planet never recovered its upright position. It simply continued spinning, adapting to the new angle as if nothing had happened. Despite the extreme tilt, Uranus remains stable. Its orbit doesn't wobble. Its rotation doesn't falter. It moves through space with the same steady patience as any other planet. Proof that even after a violent beginning, balance can return. Neptune has the strongest winds in the solar system, reaching speeds of over 1,000 miles per hour. These winds roar through the planet's upper atmosphere, driven by heat escaping from deep within. Neptune is far from the sun, receiving only a fraction of the warmth that reaches Earth. But it generates its own internal heat, a remnant of its formation. This heat rises through layers of gas, creating turbulence and driving the storms that race around the planet. One of the most famous storms, called the Great Dark Spot, was observed by the Voyager 2 spacecraft in 1989. It was a massive oval storm, similar to Jupiter's Great Red Spot. But when the Hubble Space Telescope looked for it again a few years later, the storm had vanished. Neptune's atmosphere is restless, constantly shifting, but the planet itself remains serene. It orbits quietly at the edge of the solar system, 30 times farther from the sun than Earth, moving through darkness that most sunlight never reaches. The winds may howl, but they howl into silence, surrounded by a cold so deep that nothing stirs except the motion of the planet itself. Mercury has no atmosphere to speak of, just a thin veil of atoms kicked up by solar wind and micrometeorite impacts. Without air to trap heat, the side facing the sun can reach temperatures of 800 degrees Fahrenheit, while the side in shadow drops to nearly 300 degrees below zero. The difference between day and night is one of the most extreme in the solar system, a swing of over 1,000 degrees. But this happens slowly. Because Mercury rotates so gradually, taking 59 Earth days to complete a single turn, the temperature shifts in a gentle gradient rather than a sudden shock. If you were standing on the surface, you would feel the heat rising, degree by degree as the sun climbed, then falling just as gradually as it set. There would be no wind, no sound, just the silent movement of heat radiating across ancient cratered plains. Mercury's surface is covered in impact scars from billions of years of collisions. But nothing disturbs it now. The planet is geologically dead, its interior cooled and solidified. It simply turns, locked in its 3-2 rhythm, absorbing and releasing the sun's energy in a cycle that will continue until the sun itself dies. Venus rotates in the opposite direction from most planets. While Earth, Mars, Jupiter, and the others spin counterclockwise when viewed from above their north poles, Venus spins clockwise. This is called retrograde rotation, and it's unusual. Scientists believe Venus may have been struck by a massive object early in its history, an impact so powerful that it reversed the planet's spin. Or perhaps tidal forces from the sun gradually slowed its rotation until it stopped, then started again in the opposite direction. The process would have taken millions of years, a slow reversal that left Venus turning backward. The sun rises in the west and sets in the east, though you wouldn't see it through the thick clouds. A day on Venus is longer than a year, which means the planet completes one orbit around the sun before it finishes a single rotation. Time moves strangely there, stretched and inverted, but Venus doesn't seem to mind. It continues its slow, backward spin, indifferent to the direction, focused only on the rhythm. Earth's atmosphere protects us from most of the sun's ultraviolet radiation, but it also does something else. It scatters blue light more than other colors, which is why the sky appears blue during the day. This scattering happens because blue light has a shorter wavelength, and shorter wavelengths interact more with the nitrogen and oxygen molecules in the air. At sunrise and sunset, the light has to pass through more atmosphere, scattering away even more blue and leaving the longer wavelengths of red, orange, and pink. The result is a sky that changes color depending on the angle of the sun, a daily cycle of shifting hues that we often take for granted. But this is unique to Earth. Mars has a thin atmosphere, and its sky appears butterscotch during the day and blue at sunset, the opposite of ours. Venus, with its thick clouds, sees only a hazy orange glow. On Mercury and the Moon, where there's no air, the sky is always black, even in full daylight. Earth's blue sky is a gift of our atmosphere, a reminder that we live on a planet where the air itself paints beauty across the heavens. Mars has seasons, just like Earth, because its axis is tilted at about 25 degrees. This tilt causes different parts of the planet to receive more or less sunlight throughout the year, creating cycles of warmth and cold. But because Mars takes about 687 Earth days to orbit the Sun, its seasons last nearly twice as long as ours. Spring stretches on for months. Summer lingers. Autumn and winter seem to hold the planet in stillness. During winter at the poles, carbon dioxide from the atmosphere freezes and falls as dry ice, forming polar caps that grow larger with each passing week. In summer, the ice sublimates back into gas, shrinking the caps and releasing carbon dioxide into the air. This seasonal breathing gives Mars a rhythm, a gentle expansion and contraction that mirrors the cycles of life on Earth. The planet may be cold and dry, but it's not static. It changes with the seasons, slowly and quietly, following patterns set in motion billions of years ago. Jupiter is so massive that it doesn't orbit the Sun in the traditional sense. Instead, both Jupiter and the Sun orbit a point in space called the barycenter, the center of mass between them. This point lies just above the Sun's surface, which means the Sun wobbles slightly as Jupiter pulls on it. The effect is subtle, but It's real. Over the course of Jupiter's 12-year orbit, the Sun shifts back and forth, responding to the gravitational tug of its largest planet. This wobble is how astronomers detect planets around other stars. They look for stars that move slightly, indicating the presence of an unseen companion. Jupiter's influence extends beyond its own orbit. It acts as a gravitational shepherd, protecting the inner solar system by deflecting comets and asteroids that might otherwise collide with Earth. Its massive gravity captures or redirects these objects, reducing the number of impacts we experience. In a way, Jupiter is a guardian, standing watch at the edge of the inner planets, quietly keeping us safe. Saturn's moon Titan is the only moon in the solar system with a thick atmosphere. It's composed mostly of nitrogen, with traces of methane and other hydrocarbons, and it's so dense that the surface pressure is about 50% higher than Earth's. If you stood on Titan, you could breathe the air, though it wouldn't sustain you because there's no oxygen. The sky would appear orange, tinged by the haze of methane molecules scattering sunlight. Lakes and rivers flow across Titan's surface, but they're not made of water. They're liquid methane and ethane, hydrocarbons that exist as liquids in Titan's frigid temperatures of -290 degrees Fahrenheit. Rain falls from the clouds, carving channels and filling basins, creating a hydrological cycle similar to Earth's, but made of entirely different substances. Titan is the only other world in our solar system with stable liquid on its surface. It's a strange mirror of Earth, familiar in structure, but alien in composition. The rivers flow slowly, fed by methane rain that falls gently through the thick air. Waves lap against frozen shorelines. It's a world where the landscape shifts with the seasons, where weather happens, where change is constant but measured in the slow drip of time. Uranus has 13 known rings, though they're much darker and thinner than Saturn's. They're made of ice and rock, but the particles are coated in a substance that absorbs light, making them nearly invisible except when viewed edge-on or with infrared telescopes. The rings were discovered in 1977, when astronomers noticed that a star briefly dimmed as Uranus passed in front of it. The dimming happened multiple times, in a pattern that could only be explained by the presence of narrow rings circling the planet. Each ring is separated by a gap, and within those gaps, tiny moons orbit, their gravity keeping the rings from spreading. The rings are thin, only a few miles wide, but they stretch for thousands of miles. They don't reflect much sunlight, which is why they remained hidden for so long. But they're there, circling a planet that rolls on its side, a quiet structure in a dark corner of the solar system. Neptune's largest moon, Triton, orbits the planet in the opposite direction from Neptune's rotation. This is called a retrograde orbit, and it's unusual. Most moons form from the same disk of material as their planet, so they orbit in the same direction. Triton didn't form with Neptune. It's a captured object, likely a dwarf planet from the Kuiper belt that wandered too close and was caught by Neptune's gravity. The capture process was violent, tearing Triton from its original orbit and locking it into a path around Neptune. Over millions of years, tidal forces circularized the orbit, smoothing out the chaos until Triton settled into its current path. But the retrograde orbit is slowly pulling Triton closer to Neptune. In about 3.5 billion years, it will cross the Roche limit, the point where tidal forces will tear it apart. Triton will shatter and its fragments will form a ring around Neptune, a ring that may rival Saturn's in size and brightness. For now, though, Triton remains intact, a frozen world with geysers of nitrogen shooting from its surface, orbiting backward through the darkness. Mercury's core is enormous compared to the rest of the planet. It makes up about 85% of the planet's radius, far more than any other rocky world. Earth's core, by comparison, is only about 55% of its radius. Scientists believe Mercury's large core formed because the planet was once larger, but a massive impact early in its history stripped away much of its outer layers, leaving behind the dense iron core. The impact would have vaporized rock, sending debris into space, but the core remained intact. Over time, the debris either fell back to Mercury's surface or drifted away, condensing into the thin crust that covers the planet today. The core is still partially molten, generating a weak magnetic field that protects Mercury from some of the solar wind. But the field is faint, only about 1% as strong as Earth's. It's just enough to deflect particles, creating a tiny magnetic bubble around the planet. Mercury is small and scarred, but it holds a disproportionately large heart of iron, a dense center that anchors it in space. Venus's clouds rotate much faster than the planet itself. While the planet takes 243 Earth days to complete one rotation, the clouds circle the entire planet in just 4 days. This phenomenon is called superrotation, and it's driven by high-altitude winds that race around Venus at speeds of over 200 miles per hour. The mechanism behind superrotation isn't fully understood, but it's thought to involve the transfer of angular momentum from the lower atmosphere to the upper atmosphere, accelerated by the intense heat and thick cloud cover. The clouds are made of sulfuric acid droplets, which form from sulfur dioxide released by ancient volcanic eruptions. These droplets scatter sunlight, making Venus the brightest object in our night sky after the moon. But beneath the clouds, the surface remains hidden, shrouded in a dense, hot atmosphere that crushes and bakes anything that enters. Soviet landers survived on the surface for only about an hour before succumbing to the heat and pressure. The clouds above, though, move freely, racing around the planet in a never-ending loop. Earth's magnetic field extends far into space, forming a protective bubble called the magnetosphere. This field deflects most of the solar wind, a stream of charged particles constantly flowing from the sun. Without the magnetosphere, these particles would strip away our atmosphere, eroding it over millions of years until Earth resembled Mars. The field is generated by the motion of molten iron in Earth's outer core, a process called the geodynamo. As the core rotates, it creates electric currents, which in turn generate a magnetic field. The field isn't static. It shifts and changes over time, and occasionally it flips. The north and south magnetic poles swap places, a process that happens on average every few 100,000 years. The last reversal occurred about 780,000 years ago, which means we're overdue for another flip. But reversals happen gradually, taking thousands of years to complete. So, there's no sudden shift. The magnetosphere weakens, fluctuates, and then re-establishes itself with the poles reversed. During this time, Earth's surface is exposed to more solar radiation, but life has survived every previous reversal. The field is resilient, bending but never breaking. Mars once had a global magnetic field, but it disappeared about 4 billion years ago. When the field vanished, Mars lost its protection from the solar wind. Over time, the wind stripped away much of the atmosphere, leaving behind the thin veil of gas that exists today. The surface pressure on Mars is now only about 1% of Earth's, too low to support liquid water. Any water that existed on the surface either evaporated into space or froze into the ground, forming vast reserves of ice beneath the soil. Without a magnetic field, Mars became cold and dry, a planet where the air is so thin that sound barely travels, and the sky is silent. But traces of the old field remain, locked in the rocks. Certain regions of Mars show strong magnetization, indicating that when the rocks formed, they cooled in the presence of a magnetic field. These patches of magnetism are like fossils, preserving a time when Mars was warmer, wetter, and more like Earth. The planet changed, but the memory of what it once was remains, written in stone. Jupiter's moon, Io, is the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions, lava flows, and plumes of sulfur and sulfur dioxide that shoot hundreds of miles into space. The volcanism is driven by tidal heating, a process caused by Io's elliptical orbit around Jupiter. As Io moves closer and farther from the planet, Jupiter's gravity squeezes and stretches the moon, generating friction and heat inside. This heat melts the interior, creating magma that rises to the surface and erupts. Io has no impact craters, which is unusual for a moon. Normally, craters accumulate over billions of years, marking the history of collisions with asteroids and comets. But on Io, the surface is so young, constantly renewed by volcanic activity, that craters don't have time to form. The moon glows faintly in infrared images, hot with the heat of its own internal fires. It's a world in constant motion, churning and renewing itself, unable to rest. Saturn's moon Enceladus has geysers that spray water ice into space from cracks near its south pole. These geysers shoot plumes of ice particles and water vapor hundreds of miles above the surface, fed by a subsurface ocean that lies beneath a shell of ice. The ocean is kept liquid by tidal heating, similar to Io, but less intense. Saturn's gravity flexes Enceladus as it orbits, generating just enough heat to prevent the ocean from freezing. The plumes contain organic molecules, salts, and hydrogen, all ingredients necessary for life as we know it. This discovery has made Enceladus one of the most exciting places to search for life in the solar system. The geysers form a faint ring around Saturn, called the E-ring, as the ice particles spread out along Enceladus's orbit. Some particles fall back to the moon's surface, covering it in fresh snow. Enceladus is bright, reflecting nearly 100% of the sunlight that hits it, making it one of the most reflective objects in the solar system. It's a world of ice and water, hidden beneath a frozen shell, quietly revealing its secrets through plumes that rise into the darkness. Uranus emits very little heat compared to the other gas giants. Jupiter, Saturn, and Neptune all radiate more energy than they receive from the Sun, leftover heat from their formation. Uranus, however, emits almost no excess heat. Its internal temperature is much colder than expected, and scientists aren't sure why. One theory is that the collision that knocked Uranus onto its side also released most of its internal heat, leaving the planet cold and inert. Another theory suggests that Uranus has a layer inside that blocks heat from escaping, trapping it deep within the planet. Whatever the reason, Uranus remains the coldest planet in the solar system, with atmospheric temperatures dropping as low as -371 degrees Fahrenheit. Even Neptune, farther from the Sun, is warmer because it generates internal heat. Uranus simply sits in the darkness, cold and quiet, turning on its side, reflecting the dim light of a distant sun. Neptune's atmosphere contains methane, which absorbs red light and reflects blue, giving the planet its striking azure color. The methane is mixed with hydrogen and helium, forming a deep, dynamic atmosphere where storms rage and winds howl. But beneath the visible clouds, Neptune's interior remains a mystery. Scientists believe it has a layer of water, methane, and ammonia ices surrounding a rocky core, but no spacecraft has ever penetrated deep enough to confirm this. Voyager 2 flew past Neptune in 1989, capturing images of the planet's clouds, storms, and rings. But it couldn't see below the surface. What we see is only the top layer, a skin of gas and ice that hides whatever lies beneath. Neptune is beautiful from the outside, a deep blue sphere glowing softly in the darkness, but its true nature remains hidden, locked inside layers of pressure and cold. Mercury's surface is covered in cliffs called scarps, some of them hundreds of miles long and over a mile high. These cliffs formed as the planet cooled and contracted, wrinkling like a grape drying into a raisin. As Mercury's core solidified, it shrank, pulling the crust inward and creating thrust faults where one section of crust was pushed up over another. The process was slow, taking place over billions of years, but the result is a landscape marked by long, winding ridges that cut across craters and plains. Some scarps are so tall that they cast shadows visible from space, dark lines stretching across the grey terrain. Mercury's surface hasn't changed much since the scarps formed. Without plate tectonics or volcanic activity, the planet remains frozen in time, a record of ancient forces that shaped it and then went silent. The cliffs stand as evidence of a planet that once shrank, adjusted, and settled into stillness. Venus has more volcanoes than any other planet in the solar system. Thousands of them dot the surface, ranging from small domes to massive shield volcanoes that rival Olympus Mons on Mars. Most of these volcanoes are thought to be dormant, but some may still be active. Recent observations have detected changes in the levels of sulfur dioxide in the atmosphere, suggesting that volcanic eruptions may have occurred in the past few decades. Sulfur dioxide is released during eruptions, and it rises into the atmosphere, where it combines with water vapor to form sulfuric acid. This acid condenses into clouds, which blanket the planet and trap heat, contributing to Venus's runaway greenhouse effect. The volcanoes themselves are hidden beneath the thick clouds, invisible from space except through radar imaging. Missions like Magellan mapped the surface in the 1990s, revealing a world covered in volcanic plains, lava channels, and collapsed calderas. Venus is a planet shaped by fire, a world where molten rock once flowed freely, reshaping the surface again and again. Earth's rotation is gradually slowing due to tidal friction from the moon. As the moon's gravity pulls on Earth's oceans, it creates bulges of water that move across the planet. These bulges create friction with the seafloor, which drags on Earth's rotation, slowing it down. The effect is tiny, lengthening each day by about 1.7 milliseconds per century, but over millions of years, it adds up. 400 million years ago, a day on Earth lasted only about 22 hours. Dinosaurs experienced days slightly shorter than ours. Eventually, billions of years from now, Earth's rotation will slow so much that one side will always face the moon, just as the moon already shows the same face to us. This is called tidal locking, and it's the natural end state of any system where one body orbits another. But for now, Earth continues to turn, a little slower each year, guided by the invisible pull of the moon. Mars has the largest canyon in the solar system, Valles Marineris, a rift that stretches over 2,500 miles across the planet's equator. It's nearly 4 miles deep in places, with cliffs that tower above the canyon floor. If it were on Earth, it would span the entire United States from coast to coast. The canyon formed billions of years ago when Mars was geologically active. Scientists believe it started as a crack in the crust, caused by volcanic activity in the nearby Tharsis region. As magma pushed upward, it lifted and stretched the crust, creating fractures that widened over time. Landslides, erosion, and possibly water flowing through the canyon carved the landscape into the maze of valleys we see today. Valles Marineris is now quiet, a scar on the surface of a planet that no longer trembles. But it stands as evidence of a time when Mars was alive, when forces deep inside shaped the world above. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are called the Galilean moons because Galileo Galilei discovered them in 1610. They were the first objects found orbiting another planet, proving that not everything in the sky revolved around Earth. This discovery helped shift humanity's understanding of the universe, showing that Earth was not the center of all motion. Each moon is unique. Io is volcanic, constantly resurfacing itself. Europa has a subsurface ocean beneath a shell of ice, making it one of the most likely places to find life. Ganymede is the largest moon in the solar system, bigger even than Mercury, and it has its own magnetic field. Callisto is ancient and cratered, its surface unchanged for billions of years. Together, they orbit Jupiter in a resonance, a gravitational dance where their orbits are mathematically linked. For every 4 orbits Io completes, Europa completes 2, and Ganymede completes 1. This resonance stabilizes the system, preventing the moons from colliding or drifting away. Saturn's rings cast shadows on the planet's surface during certain times of the year. As Saturn orbits the Sun, the angle of sunlight changes, causing the rings to tilt and cast long, dark shadows across the northern or southern hemisphere. These shadows are most visible during Saturn's equinox, when the Sun shines directly on the equator and the rings appear edge-on. At this time, the rings are so thin that they nearly disappear from view, visible only as a faint line cutting across the planet. But the shadows remain, a reminder of the structure circling above. The shadows shift and change with the seasons, moving across the clouds as Saturn completes its 29-year orbit around the Sun. Watching Saturn through a telescope over time, you can see the rings open and close, tilting toward or away from us, revealing different perspectives of the same glowing structure. Uranus has 27 known moons, most of them named after characters from the works of William Shakespeare and Alexander Pope. The largest, Titania, is only about half the size of Earth's moon, and the smallest are just a few miles across. Many of these moons are icy and cratered, marked by ancient impacts, but some show signs of past activity. Miranda, one of the smaller moons, has a surface unlike any other. It's covered in towering cliffs, some over 3 miles high, and strange, grooved terrain that looks like it was assembled from mismatched pieces. Scientists believe Miranda may have been shattered by an impact and then reassembled, the fragments coming back together under their own gravity, but never quite fitting perfectly. The result is a moon that looks broken and stitched back together, a world that carries the scars of a violent past but remains intact. Neptune's moon Triton is one of the coldest objects in the solar system, with surface temperatures around -391 degrees Fahrenheit. Despite the extreme cold, Triton is geologically active. Geysers of nitrogen gas erupt from beneath its icy surface, shooting plumes up to 5 miles high. The geysers are powered by sunlight, which warms the subsurface ice just enough to vaporize nitrogen trapped below. The gas builds pressure until it breaks through the surface, creating dark streaks as dust and debris are carried along with the plume. Triton's surface is young, with few impact craters, suggesting that it has been resurfaced relatively recently by geological processes. The moon is tidally locked to Neptune, always showing the same face to the planet, just as Earth's moon does to us. But Triton's retrograde orbit means it's slowly spiraling inward, doomed to be torn apart in the distant future. For now, though, it remains whole, erupting quietly in the freezing darkness. Mercury has water ice at its poles, despite being the closest planet to the Sun. The ice is hidden in permanently shadowed craters, where temperatures never rise above -300 degrees Fahrenheit. Sunlight never reaches these craters because Mercury's axis is almost perfectly upright, with no tilt. On Earth, the tilt of our axis creates seasons and ensures that sunlight reaches the poles at least part of the year. But Mercury has no seasons. The poles remain in perpetual darkness, creating cold traps where water ice can survive for billions of years. The ice likely came from comets that collided with Mercury long ago, delivering water that froze and never melted. Radar observations have confirmed the presence of ice in dozens of craters near the North and South poles. It's strange to think of a planet so close to the Sun harboring ice. But the universe is full of such contradictions. Mercury is both the hottest and coldest place in the inner solar system, depending on where you stand. Venus has no moons and no rings. It orbits the Sun alone, unaccompanied by any natural satellite. Scientists aren't entirely sure why Venus lacks a moon. One theory is that Venus once had a moon, but it was destroyed by a collision or drawn into the planet by tidal forces. Another theory suggests that Venus's slow rotation prevented a moon from forming in the first place. When planets form, they're surrounded by disks of gas and dust from which moons can coalesce. But if the planet rotates too slowly, the disk disperses before a moon can form. Venus's rotation is so slow that it may have missed its chance. Or perhaps the Sun's gravity, so strong this close to the star, prevented any debris from settling into orbit. Whatever the reason, Venus remains solitary, a planet that moves through space without a companion. Earth is the only planet in the solar system where water exists in all three states, solid, liquid, and gas, on the surface at the same time. Ice covers the polar caps and high mountains. Liquid water fills oceans, lakes, and rivers. Water vapor drifts through the atmosphere, condensing into clouds and falling as rain or snow. This cycle, called the hydrological cycle, is driven by the Sun's energy, which evaporates water from the surface, lifts it into the air, and then allows it to condense and fall back down. The process redistributes water across the planet, carving landscapes, nurturing life and regulating climate. Other planets have water, but it's locked in ice or hidden beneath the surface. Only on Earth does water flow freely, shaping the world in real time. It's one of the reasons Earth is so dynamic, so full of change and life. Water is the medium through which energy moves, and it connects everything. Mars has two small moons, Phobos and Deimos, both irregularly shaped and heavily cratered. They're thought to be captured asteroids, objects that once orbited the Sun independently but were caught by Mars's gravity. Phobos, the larger of the two, orbits so close to Mars that it completes 3 full orbits in a single Martian day. It's slowly spiraling inward, moving about 6 feet closer to the planet every 100 years. In about 50 million years, Phobos will either collide with Mars or be torn apart by tidal forces, forming a ring around the planet. Deimos, smaller and farther out, orbits more slowly and will eventually drift away. The two moons are dark, reflecting only about 6% of the sunlight that hits them. They're composed of carbon-rich rock, similar to asteroids found in the outer solar system. Phobos and Deimos are not graceful companions. They're irregular, battered, and temporary. But they're Mars's only moons, and they circle the planet faithfully for now. Jupiter has at least 79 known moons, and more are discovered regularly as telescopes and spacecraft improve. Most of these moons are small, irregular chunks of rock and ice captured by Jupiter's gravity. The 4 Galilean moons dominate the system, but the smaller moons tell a story of chaos and capture. Many of them orbit in retrograde, moving opposite to Jupiter's rotation, which indicates they were captured rather than formed from the same disk of material as the planet. These moons are thought to be asteroids or comets that wandered too close to Jupiter and became trapped in its gravitational well. Some orbit in highly elliptical paths, swinging far from the planet before returning. Others cluster in groups, families of moons that may have once been a single object shattered by collision. Jupiter's moon system is a miniature solar system, diverse and complex, held together by the overwhelming gravity of the largest planet. Saturn's moon Mimas has a giant crater called Herschel, which covers about 1/3 of the moon's diameter. The crater is so large that the impact that created it nearly destroyed Mimas entirely. The force of the collision sent shockwaves through the moon, fracturing the opposite side and leaving it on the verge of breaking apart. But Mimas held together, and the crater remained, a permanent scar. Herschel is about 86 miles wide and 6 miles deep, with a central peak that rises almost 4 miles above the crater floor. The crater gives Mimas a distinctive appearance, making it resemble the Death Star from Star Wars. But Mimas is no artificial construct. It's a small, icy moon, only 246 miles in diameter, circling Saturn in a quiet, stable orbit. The crater is a reminder of a moment of violence, but Mimas survived, and it continues to orbit peacefully, unchanged for millions of years. Uranus's rings are narrow and dark, composed of particles that are likely boulder-sized, rather than the fine ice particles that make up Saturn's rings. The rings are kept in place by small shepherd moons, whose gravity prevents the particles from spreading. The rings were discovered by accident in 1977, when astronomers noticed that a star dimmed multiple times as Uranus passed in front of it. Each dimming corresponded to a ring crossing the line of sight, revealing a structure that had been invisible until then. The rings are faint and difficult to see, even with powerful telescopes. But they're there, circling Uranus in thin bands. The shepherd moons, Cordelia and Ophelia, orbit just inside and outside the brightest ring, their gravity sculpting the structure and keeping it stable. Without these moons, the rings would gradually spread and dissipate, but for now they remain confined, narrow paths of darkness around a tilted world. Neptune's rings are faint and incomplete, consisting of several arcs rather than continuous bands. These arcs are named liberty, equality, fraternity, and courage, and they're thought to be held in place by the gravitational influence of Neptune's moon Galatea. The arcs are made of dust-sized particles that reflect very little light, making them difficult to detect. They were discovered when astronomers observed Neptune passing in front of a star and noticed brief, irregular dimmings in the star's light. The rings are unstable over long timescales, and without the gravitational confinement provided by Galatea, they would spread out and disappear. For now, they persist, faint traces of material orbiting Neptune, visible only under specific conditions and angles. Mercury completes its orbit around the Sun in just 88 Earth days, making it the fastest planet in the solar system. Its year is shorter than its day, which means Mercury orbits the Sun more than once before it completes a single rotation. This creates an unusual relationship between time and motion. If you lived on Mercury, you would experience fewer days than years, because a day is defined by the Sun rising and setting, and that happens so slowly compared to the planet's orbit. The rapid orbit is caused by Mercury's proximity to the Sun. It travels along its elliptical path at an average speed of about 105,000 miles per hour, faster than any other planet. The gravitational pull of the Sun is so strong, this close, that Mercury has no choice but to race around, locked in a pattern that has repeated for billions of years. Venus's atmosphere is so thick that it exerts 93 times more pressure at the surface than Earth's atmosphere. This is equivalent to being nearly a mile underwater on Earth. The pressure is so intense that it has crushed every spacecraft that has landed on Venus, flattening metal and glass within hours. The atmosphere is made mostly of carbon dioxide, which traps heat and creates a runaway greenhouse effect. The surface temperature is about 900 degrees Fahrenheit, hot enough to melt lead, but the pressure and heat are distributed evenly across the planet. There are no cold spots, no relief, just a constant, crushing environment that remains the same day and night, year after year. Venus is inhospitable, but it's also stable. The conditions don't fluctuate. They simply are, unchanging and unyielding. Earth's atmosphere is about 78% nitrogen, 21% oxygen, and 1% other gases, including argon and carbon dioxide. This mixture is unique in the solar system. Nitrogen is inert, which means it doesn't react easily with other substances, making it a stable filler for the atmosphere. Oxygen is reactive, and it only exists in large quantities because life on Earth produces it. Plants, algae, and cyanobacteria release oxygen during photosynthesis, constantly replenishing the supply. Without life, Earth's oxygen would gradually disappear, reacting with rocks and other materials until the atmosphere resembled that of Venus or Mars. But life persists, and so does the oxygen, creating a feedback loop that has sustained itself for billions of years. The atmosphere is not just a layer of gas. It's a living system, maintained by the organisms that depend on it. Mars's atmosphere is mostly carbon dioxide, with traces of nitrogen and argon. The air is so thin that it can't trap much heat, which is why temperatures on Mars can swing by over 150 degrees Fahrenheit between day and night. During the day, the sun warms the surface, but as soon as it sets, the heat radiates back into space, and the temperature plummets. The lack of a thick atmosphere also means there's no protection from radiation. Cosmic rays and solar particles strike the surface unimpeded, making Mars a hostile environment for life as we know it. But the thin atmosphere isn't entirely useless. It creates weather, including dust storms, that can grow large enough to cover the entire planet. These storms lift dust into the air, where it can stay suspended for weeks, blocking sunlight and cooling the surface. Mars's atmosphere is tenuous, but it's dynamic, constantly shifting and responding to the changing seasons. Jupiter's atmosphere doesn't have a solid surface. As you descend, the gas becomes denser and hotter, gradually transitioning into a liquid state. There's no clear boundary between the atmosphere and the interior, just a continuous change in pressure and temperature. Eventually, the pressure becomes so intense that hydrogen is compressed into a metallic state, where it conducts electricity like metal. This layer of metallic hydrogen surrounds Jupiter's core and generates the planet's powerful magnetic field. The field extends millions of miles into space, creating a magnetosphere that protects Jupiter's moons from the solar wind. But deep inside, beneath the metallic hydrogen, lies the core, a dense ball of rock and ice about 10 times the mass of Earth. This core is thought to be the seed around which Jupiter formed, accreting gas from the solar nebula until it became the giant we see today. Jupiter is a planet of layers, each one blending into the next, a structure built from the inside out. Saturn's atmosphere, like Jupiter's, is composed mostly of hydrogen and helium, with traces of methane, ammonia, and water vapor. The methane absorbs red light, giving Saturn a pale yellow color. The atmosphere is turbulent, with wind speeds reaching over 1,000 miles per hour near the equator. These winds are driven by heat escaping from Saturn's interior, heat left over from the planet's formation. Saturn radiates more energy than it receives from the Sun, a sign that it's still cooling. The excess heat creates convection, rising currents of warm gas that drive the winds and generate the storms visible in the upper atmosphere. One of the most striking features is a hexagonal pattern at the North Pole, a jet stream that forms a six-sided shape thousands of miles across. The hexagon has been stable for decades, rotating with the planet, a geometric oddity in a chaotic sea of gas. No one fully understands why it forms, but it remains, turning slowly, perfectly symmetrical. Uranus's atmosphere is made of hydrogen, helium, and methane, with the methane giving the planet its blue-green color. The methane absorbs red and infrared light, reflecting blue back into space. But compared to Jupiter and Saturn, Uranus's atmosphere is relatively calm. There are few visible storms, and the clouds are faint, hidden beneath a haze of methane. The lack of internal heat means there's less energy to drive weather, so the atmosphere is subdued, quiet. Occasionally, storms do appear, bright spots that emerge near the edges of the planet and then fade. These storms are driven by the changing seasons, as Uranus's tilted axis brings different parts of the planet into sunlight. But most of the time, Uranus appears featureless, a smooth blue sphere that rotates on its side, unmarked and serene. Neptune's atmosphere is the most dynamic of the ice giants. Despite being farther from the Sun than Uranus, Neptune has stronger winds, more storms, and a richer blue colour. The methane in its atmosphere absorbs red light, but scientists believe there's an additional, unknown component that enhances the blue, making Neptune appear deeper and more vibrant than Uranus. The winds on Neptune are the fastest in the solar system, reaching over 1,000 miles per hour. These winds create dark storms that appear and disappear over the course of a few years. The most famous, the Great Dark Spot, was observed by Voyager 2 but had vanished by the time Hubble looked for it again. Neptune's atmosphere is restless, constantly churning, driven by internal heat that rises from the planet's core. The energy creates motion, and the motion creates beauty, a swirling, ever-changing canvas of clouds and storms. Mercury has a very thin exosphere, a layer of atoms so sparse that they barely interact with each other. The exosphere is constantly replenished by atoms knocked off the surface by the solar wind and micrometeorite impacts. These atoms drift upward, hang in space for a while, and then either fall back to the surface or are blown away by the solar wind. The exosphere contains sodium, potassium, and hydrogen, among other elements, and it changes depending on Mercury's position in its orbit. When Mercury is closest to the Sun, the solar wind is stronger, stripping more atoms from the surface. When it's farther away, the exosphere thins. This constant exchange between the surface and space creates a dynamic, ever-shifting boundary, a reminder that Mercury is not a static world, but a place where motion and change occur, even if slowly. Venus's thick atmosphere traps so much heat that the temperature at the surface is nearly uniform, regardless of latitude or time of day. There's no difference between the equator and the poles, no variation between day and night. The greenhouse effect is so strong that heat is distributed evenly by the dense air, creating a planet-wide sauna. The clouds above reflect most of the sunlight, so the surface is dim, lit only by the diffused glow that filters through. But the heat remains, constant and inescapable. Venus is a world where equilibrium has been reached, where the forces of heat and pressure balance perfectly, creating conditions that never change. It's both stable and oppressive, a planet locked into a state from which there's no easy escape. Earth's axis is tilted at about 23.5 degrees, and this tilt is what gives us seasons. As the planet orbits the Sun, different parts of the world receive more or less direct sunlight throughout the year. When the northern hemisphere tilts toward the Sun, it experiences summer, while the southern hemisphere has winter. 6 months later, the roles reverse. This cycle repeats endlessly, a rhythm that shapes everything from weather patterns to migration routes to the growth of plants. The tilt also affects the length of days. In summer, the days are longer because the Sun spends more time above the horizon. In winter, the days shorten and nights stretch longer. Near the poles, the effect is extreme. During summer, the Sun never sets, creating months of continuous daylight. During winter, it never rises, plunging the region into darkness. The tilt is stable, maintained by the gravitational influence of the Moon, which acts as a stabilizer. Without the Moon, Earth's tilt would wobble chaotically, causing extreme and unpredictable climate changes. But the Moon is there, holding us steady, keeping the seasons predictable and life sustainable. Mars has polar ice caps made of water ice and frozen carbon dioxide, commonly known as dry ice. During the Martian winter, temperatures drop so low that carbon dioxide from the atmosphere freezes and falls as snow, accumulating on the polar caps. The caps grow larger, spreading across the poles in bright white layers. When spring arrives and the temperatures rise, the dry ice sublimates, turning directly from solid to gas without melting. The carbon dioxide returns to the atmosphere, and the caps shrink. Beneath the seasonal layer of dry ice lies a permanent cap of water ice, which remains frozen year-round. The water ice is thick, in some places over a mile deep, and it represents a significant reservoir of water on Mars. If this ice were melted, it could cover the entire planet in a layer of liquid about 100 feet deep. The polar caps are dynamic, breathing with the seasons, expanding and contracting in a rhythm that has continued for millions of years. They're one of the most visible signs that Mars is not entirely dead, but still responds to the cycle of time. Jupiter has a faint ring system, much thinner and darker than Saturn's. The rings are made of dust particles kicked up from Jupiter's small inner moons by meteorite impacts. As tiny rocks strike the moons, they send plumes of dust into space, and this dust settles into orbit around Jupiter, forming a diffuse ring. The main ring is only about 4,000 miles wide and less than 20 miles thick, so thin that it's nearly invisible except when backlit by the sun. The rings were discovered by Voyager 1 in 1979, when the spacecraft looked back at Jupiter and saw a faint glow surrounding the planet. Before that, no one knew Jupiter had rings at all. The rings are temporary, constantly renewed by fresh dust from impacts, but also constantly depleted as particles spiral into Jupiter's atmosphere. They exist in a state of equilibrium, a balance between creation and destruction that keeps them faintly visible but never substantial. Saturn's moon Titan has seasons, just like Earth, because Saturn's axis is tilted at about 27 degrees. As Saturn orbits the Sun, different parts of Titan receive more or less sunlight, creating cycles that last about 7.5 Earth years each. During Titan's summer, the Sun warms the hemisphere facing it, causing methane to evaporate from the lakes and rise into the atmosphere. Clouds form and rain falls, filling the lakes again. During winter, the opposite happens. The hemisphere cools and methane condenses, freezing out of the atmosphere. The lakes shrink and some dry up entirely, leaving behind crusts of frozen hydrocarbons. The seasons drive a hydrological cycle that mirrors Earth's water cycle, but with methane and ethane instead of water. Titan's thick atmosphere distributes heat slowly, so the seasonal changes are gradual and gentle. The landscape transforms over years, not days, shifting between wet and dry in a rhythm governed by Saturn's slow orbit around the Sun. Uranus's magnetic field is tilted at nearly 60 degrees from its rotational axis, and it's also offset from the planet's center. This means the magnetic field doesn't align with the poles the way Earth's does. Instead, it wobbles and shifts as Uranus rotates, creating a chaotic and asymmetric magnetosphere. The field lines are twisted and irregular, and they flip direction as the planet turns. This unusual configuration is thought to be caused by the way Uranus's magnetic field is generated. Instead of originating deep in the core like Earth's, Uranus's field may be produced in a layer of slushy ice and water closer to the surface. This layer conducts electricity and generates magnetism, but because it's off-center, the field is skewed. The result is a magnetosphere unlike any other, one that pulsates and shifts, constantly changing shape as Uranus rolls through space. It's a reminder that not all planets follow the same rules, that each one has its own quirks and mysteries. Neptune's magnetic field is also tilted at about 47 degrees from its rotational axis, similar to Uranus. This suggests that both ice giants generate their magnetic fields in a similar way, through layers of conducting material beneath their atmospheres, rather than deep in their cores. The tilt causes Neptune's magnetosphere to wobble as the planet rotates, creating a constantly shifting environment around the planet. The field is strong enough to trap charged particles from the solar wind, creating radiation belts similar to Earth's Van Allen belts. These belts can be hazardous to spacecraft, bombarding them with high-energy particles. But Neptune is so far from the Sun that the solar wind is weak by the time it reaches the planet, so the radiation belts are less intense than Jupiter's or Saturn's. Neptune's magnetic field is strange and complex, a product of the planet's internal structure, but it serves the same purpose as any other magnetic field. It deflects the solar wind, protecting the planet and its moons from erosion. Mercury's surface is covered in a fine layer of dust called regolith, created by billions of years of micrometeorite impacts. These tiny rocks, some no larger than grains of sand, constantly bombard the surface, grinding rock into powder. The regolith is dark and grey, giving Mercury its muted appearance. Unlike the Moon, which also has regolith, Mercury's surface is more reflective because the constant solar wind keeps the dust stirred and prevents it from compacting. The regolith is only a few inches thick in most places, but in some areas it can be several feet deep. Beneath it lies solid bedrock, ancient and unchanged since the planet's formation. Walking on Mercury's surface would feel like walking on powder, each step sinking slightly, leaving footprints that would last for millions of years. There's no wind or water to erase them, no erosion to smooth them away. Only the slow rain of micrometeorites, gradually filling them in grain by grain. Venus rotates so slowly that its thick atmosphere circulates much faster than the planet itself. This creates a phenomenon where the weather moves independently of the surface. Clouds race around the planet, completing a full circuit in just 4 days, while the ground beneath takes 243 days to rotate once. The result is a world where the sky and the land are disconnected, moving at different speeds. Standing on Venus, you would feel no wind at the surface because the thick air at ground level is nearly still. But far above, in the upper atmosphere, hurricane-force winds roar, carrying clouds and heat around the planet. The disconnect between surface and sky is one of Venus's strangest features, a reminder that atmospheres can behave in ways completely independent of the solid world below. Earth has 5 major ocean gyres, large systems of rotating currents that circulate water around the ocean basins. These gyres are driven by wind, the Coriolis effect, and differences in water temperature and salinity. They move slowly, taking years to complete a full rotation, but they transport vast amounts of heat and nutrients across the planet. The Gulf Stream, part of the North Atlantic Gyre, carries warm water from the tropics to the North Atlantic, moderating the climate of Western Europe. Without it, places like Ireland and Scotland would be much colder. The gyres also collect floating debris, including plastic, which accumulates in the centers where the currents converge. These areas, sometimes called garbage patches, are evidence of how currents move and concentrate materials over time. The gyres are ancient, driven by forces that have existed as long as the oceans themselves, circulating endlessly, connecting distant parts of the world through the slow movement of water. Mars has dust devils, small whirlwinds that form when the ground heats up during the day. As the surface warms, it heats the air above it, causing it to rise. Cooler air rushes in to replace it, and if the conditions are right, the air begins to spin. The spinning column picks up dust, creating a visible funnel that can be hundreds of feet tall. Dust devils on Mars can last for minutes or even hours, wandering across the plains, leaving dark trails where they've disturbed the dust. They're not dangerous, just gentle swirls of air and dust, driven by the weak but persistent heat of the Martian sun. Rovers on Mars have photographed dust devils passing nearby, and some have even been struck by them, getting a brief cleaning as the winds blow dust off their solar panels. It's one of the few times Mars's thin atmosphere creates visible motion, a reminder that even in a place as still as Mars, the air is not entirely dead. Jupiter's moon Europa has a surface made almost entirely of water ice, and beneath that ice lies a global ocean. The ocean is thought to be about 60 to 90 miles deep, far deeper than any ocean on Earth. It's kept liquid by tidal heating, the same process that drives Io's volcanoes. As Europa orbits Jupiter, the planet's gravity squeezes and stretches. The moon, generating heat through friction. This heat melts the ice from below, maintaining a layer of liquid water between the frozen surface and the rocky interior. The surface itself is covered in long cracks and ridges, evidence of the ice shifting and breaking as the ocean moves beneath. Some cracks appear reddish or brownish, colored by salts and minerals that have risen from the ocean and been exposed to radiation. Europa is one of the most promising places in the solar system to search for life. The ocean is salty, it's in contact with rock, and it has a source of heat. All the ingredients are there. Whether life actually exists is unknown, but the possibility makes Europa a world of profound interest. Saturn's moon Dione has bright, wispy streaks across its surface, long thought to be ice deposits. Recent observations suggest they might actually be cliffs, exposed walls of ice that reflect sunlight more brightly than the darker plains surrounding them. Dione is tidally locked to Saturn, always showing the same face to the planet, and the cliffs are concentrated on the side that faces away. This pattern suggests they were created by tectonic activity, possibly driven by tidal heating when Dione's orbit was more elliptical. Over time, the orbit circularized, the heating stopped, and the tectonic activity ceased. Dione is now geologically quiet, a frozen world where nothing moves except the slow drift of micrometeorites adding to the surface dust. But the cliffs remain, bright lines cutting across dark plains, evidence of a time when Dione was alive with motion. Uranus's moon Ariel has the brightest surface of any of Uranus's moons. It reflects about 40% of the sunlight that hits it, which is high for an object so far from the sun. The brightness comes from fresh ice, relatively free of the dark, radiation-damaged material that coats older surfaces. Ariel has valleys and ridges, suggesting that it was once geologically active. Tectonic forces, possibly driven by tidal heating, cracked the surface and allowed fresh ice to rise from below. The ice froze quickly, preserving the bright, clean appearance. Aurial's surface is also covered in impact craters, but they're fewer and smaller than expected for a moon of its age. This suggests that the surface was resurfaced relatively recently, erasing older craters and leaving behind a landscape that looks younger than it is. Aurial is quiet now, frozen and still, but its bright surface tells the story of a time when it was active and changing. Neptune's moon Proteus is one of the largest irregularly shaped objects in the solar system. It's about 260 miles across, but instead of being round, it's lumpy and elongated, with a heavily cratered surface. Proteus is so large that it's close to the threshold where gravity would pull it into a sphere, but it hasn't quite reached that point. The largest crater on Proteus, called Pharos, is about 150 miles wide, nearly as large as the moon itself. The impact that created Pharos almost shattered Proteus entirely, but the moon held together, and the crater remained. Proteus orbits close to Neptune, closer even than Triton, and it's thought to have formed from debris left over from Neptune's formation. It's a relic, a piece of the early solar system that never quite became a planet or a proper moon, just a chunk of rock and ice that found a stable orbit and stayed there. Mercury's orbit is not a perfect ellipse. It's slightly oval, and the point of closest approach to the Sun shifts over time, a phenomenon called precession. For centuries, astronomers noticed that Mercury's orbit didn't match the predictions made by Newton's laws of gravity. The orbit precessed slightly faster than it should, and no one could explain why. The discrepancy was tiny, only about 43 arcseconds per century, but it was measurable and puzzling. The mystery wasn't solved until Einstein published his theory of general relativity in 1915. According to relativity, gravity is not just a force, but a curvature of space-time, and massive objects like the Sun warp the space around them. Mercury, being so close to the Sun, experiences this curvature more strongly than other planets, and the effect causes its orbit to precess at the observed rate. Mercury's orbit was the first test of general relativity, and it passed perfectly. The planet's motion confirmed one of the most important theories in physics, proving that gravity is not what we thought it was. Venus has lightning, though it's different from Earth's. On Earth, lightning is generated by thunderstorms, where ice particles collide in clouds and create static electricity. Venus has no water clouds, but it does have lightning, possibly generated by volcanic eruptions or by chemical reactions in the thick atmosphere. The lightning flashes are rare and difficult to detect, but spacecraft have picked up radio signals that indicate electrical discharges. The flashes are brief, lasting only milliseconds, and they occur high in the atmosphere, far above the surface. Venus's lightning is a mystery, one of many phenomena on the planet that scientists are still trying to understand. It's a reminder that atmospheres are complex, capable of generating electricity and energy in ways that depend on their unique chemistry and conditions. Earth's oceans absorb a significant amount of carbon dioxide from the atmosphere, helping to regulate the planet's climate. Phytoplankton, tiny photosynthetic organisms that drift in the surface waters, consume carbon dioxide and produce oxygen, just like plants on land. When phytoplankton die, they sink to the ocean floor, carrying the carbon with them and locking it away in sediments for millions of years. This process, called the biological pump, has been removing carbon from the atmosphere for billions of years, helping to keep Earth's climate stable. The oceans act as a buffer, absorbing excess carbon dioxide and preventing runaway greenhouse effects like the one that occurred on Venus. But the system has limits. As carbon dioxide levels rise, the oceans become more acidic, which can harm marine life and disrupt the biological pump. The balance is delicate, maintained by the slow, steady work of countless tiny organisms. Mars has layered deposits at its poles, visible in the cliffs, where the ice has been cut away by erosion. These layers are made of ice and dust, deposited over millions of years as the planet's climate changed. Each layer represents a period of accumulation, followed by a period of erosion, creating a record of Martian climate history. The layers vary in thickness and composition, reflecting changes in temperature, atmospheric pressure, and the amount of dust in the air. Scientists study these layers the way geologists study tree rings or ice cores on Earth, reading the history of the planet in the patterns of light and dark. The layers tell a story of a planet that has cycled through ice ages and warmer periods, driven by changes in its orbit and axial tilt. Mars's climate is not static. It changes over long timescales, and the polar layers preserve that history, waiting to be read. Jupiter's moon Callisto is the most heavily cratered object in the solar system. Its surface is ancient, virtually unchanged for billions of years. Unlike Io, which is constantly resurfacing, or Europa, which has a young surface, Callisto has been geologically dead since shortly after it formed. The craters cover nearly every square mile, overlapping and intersecting, creating a landscape that looks like a frozen record of impacts stretching back to the dawn of the solar system. The largest crater, Valhalla, is over 1,800 miles across, surrounded by concentric rings that spread outward like ripples in a pond. The impact that created Valhalla was so powerful that it sent shock waves through Callisto's entire structure, but the moon absorbed the energy and remained intact. Callisto is quiet now, orbiting Jupiter in a stable path, undisturbed by tidal heating or volcanic activity. It simply exists, a monument to time and impacts, a world that has seen everything and survived. Saturn's moon Rhea has a thin atmosphere made of oxygen and carbon dioxide, one of the few moons in the solar system with any atmosphere at all. The atmosphere is extremely thin, millions of times less dense than Earth's, but it's there, generated by the breakdown of water ice on Rhea's surface. Radiation from Saturn's magnetosphere strikes the ice, splitting water molecules into hydrogen and oxygen. The hydrogen escapes into space, being too light to be held by Rhea's weak gravity, but the oxygen remains, forming a tenuous layer around the moon. Carbon dioxide is also present, though scientists aren't sure where it comes from. It may be released from the interior, or it may be produced by chemical reactions on the surface. Rhea's atmosphere is so thin that it's more of an exosphere, a cloud of gas that barely interacts with itself. But it's enough to be detected and studied. Uranus's moon Oberon is the second largest of Uranus's moons, and it has one of the oldest surfaces. The surface is covered in craters, some of them ancient, with dark material filling their floors. The dark material is thought to be a mixture of ice and rock, possibly brought to the surface by impacts or volcanic activity. Oberon also has a large mountain near its south pole, about 4 miles high, which is unusual for an icy moon. the mountain may be a remnant of tectonic activity, or it may have been created by an impact that pushed material upward. Oberon is geologically quiet now, frozen and stable, but its surface preserves clues to a more active past. It's a world that has settled into stillness, where change happens only through the slow accumulation of impacts, adding craters one at a time over millions of years. Neptune's moon, Nereid, has one of the most eccentric orbits in the solar system. Its distance from Neptune varies wildly, from about 800,000 miles at its closest to nearly 6 million miles at its farthest. This extreme ellipse suggests that Nereid is a captured object, possibly a Kuiper belt object that wandered too close to Neptune and was caught by the planet's gravity. The orbit is also inclined, tilted at about 27 degrees from Neptune's equator, which supports the idea that Nereid didn't form with the planet. It's small, only about 210 miles across, and its surface is heavily cratered. Nereid is thought to be made of ice and rock, similar to other captured moons, and it reflects about 20% of the sunlight that hits it, giving it a moderately bright appearance. Nereid is a wanderer, caught in a strange orbit, circling Neptune in a path that takes it far from the planet, and then brings it back again. Mercury has a very weak magnetic field, only about 1% as strong as Earth's. This field is generated by the planet's molten outer core, which circulates and creates a dynamo effect. But because Mercury is small and its core is cooling, the dynamo is weak and the magnetic field is correspondingly faint. The field is just strong enough to create a small magnetosphere, a bubble of magnetic influence that deflects some of the solar wind. Without this field, the solar wind would strike Mercury's surface directly, stripping away atoms and gradually eroding the planet. The magnetosphere is asymmetric, stronger on the side facing the sun and weaker on the night side, shaped by the constant pressure of the solar wind. Mercury's magnetic field is a fragile shield, barely adequate to protect the planet, but it's there, a sign that Mercury's core is still at least partially molten. Venus has almost no magnetic field at all. The planet's core may still be molten, but without a significant rotation, there's no dynamo effect to generate magnetism. Venus rotates so slowly that the liquid metal in its core doesn't circulate fast enough to create a field. As a result, Venus has no magnetosphere, no protection from the solar wind. The solar wind strikes the planet's upper atmosphere directly, stripping away atoms and ions. Over billions of years, this process may have removed much of Venus's original atmosphere, though the thick atmosphere that remains suggests that volcanic outgassing has replenished it. Venus is vulnerable, exposed to space in a way that Earth is not, but the planet has endured. Its thick atmosphere provides some protection, and the solar wind, though constant, is not strong enough to strip the atmosphere away quickly. Earth's magnetic field flips irregularly, with no predictable pattern. The last reversal occurred 780,000 years ago, and before that, reversals happened on average every few 100,000 years. During a reversal, the field weakens, becomes chaotic, and then re-establishes itself with the poles reversed. The process can take thousands of years, and during that time, Earth's protection from cosmic radiation is reduced. However, life has survived every reversal, and there's no evidence that reversals cause mass extinctions. The atmosphere provides some shielding, and most organisms are resilient enough to withstand the increased radiation. The magnetic field is not static. It shifts, fluctuates, and occasionally flips, a reminder that even the forces we consider stable are part of a dynamic, ever-changing system. Mars lost its magnetic field about 4 billion years ago, and the loss had profound consequences. Without a magnetic field, the solar wind began stripping away the atmosphere, molecule by molecule. Over millions of years, Mars's atmosphere thinned, the surface pressure dropped, and liquid water could no longer exist. The rivers dried up, the lakes evaporated, and the planet became the cold, dry world we see today. The loss of the magnetic field was likely caused by the cooling of Mars's core, which stopped the dynamo effect. Mars is smaller than Earth, and smaller planets cool faster. Once the core solidified, the magnetic field disappeared, and Mars was left defenseless. The planet's transformation from a warm, wet world to a cold desert took millions of years, but it was irreversible. Mars is a cautionary tale, a reminder of what can happen when a planet loses its magnetic shield. Jupiter's moon. Ganymede is the only moon in the solar system with its own magnetic field. The field is generated by a liquid iron core deep inside the moon, similar to Earth's. Ganymede's core is kept warm by tidal heating, though the heating is much weaker than on Io or Europa. The magnetic field is about 1% as strong as Earth's, but it's enough to create a small magnetosphere around the moon. This magnetosphere interacts with Jupiter's much larger magnetosphere, creating a complex region of magnetic fields and charged particles. Ganymede's field protects its surface from some of Jupiter's intense radiation, creating a safer environment than on the other Galilean moons. The field is a sign that Ganymede is still geologically active, at least in its deep interior, even though its surface appears old and cratered. Saturn's moon Enceladus has a warm region near its south pole, where temperatures are about 30 degrees Fahrenheit, warmer than the rest of the moon. This might not sound warm, but on a world where the average temperature is minus 330 degrees Fahrenheit, it's significant. The warmth is caused by tidal heating, the same process that drives the geysers. As Enceladus orbits Saturn, the planet's gravity flexes the moon, generating heat through friction. The heat concentrates near the South Pole, where the crust is thinner and the geysers erupt. The warm region is visible in infrared images, glowing softly against the cold background. It's a sign that Enceladus is not entirely frozen, that deep beneath the ice, liquid water exists, heated by forces that will continue for millions of years. Uranus's moon Miranda has the most varied terrain of any moon in the solar system. Its surface is a patchwork of different features, including smooth plains, jagged cliffs, and strange grooved regions called coronae. The coronae look like racetrack ovals, with parallel ridges running along their edges. Scientists believe they formed when warm ice rose from Miranda's interior, creating domed regions that then collapsed and fractured. The cliffs, some over 3 miles high, are the tallest known cliffs in the solar system, relative to the size of the body. Standing at the top of one of these cliffs, you could see the curve of Miranda's horizon, a small world with a dramatic landscape. Miranda's surface suggests a violent past, possibly including a collision that shattered the moon and then allowed it to reassemble. The result is a moon that looks like it was put together from spare parts, each piece telling a different story. Neptune's moon Triton has a surface composed of frozen nitrogen, water ice, and methane. The nitrogen ice is reflective, giving Triton a bright, pinkish appearance. The surface is young, with few craters, indicating that it has been resurfaced relatively recently by geological activity. The geysers that erupt from the surface are evidence of ongoing processes beneath the ice. Triton also has a thin atmosphere, made mostly of nitrogen with traces of methane. The atmosphere is tenuous, about 100,000 times less dense than Earth's, but it's enough to create winds that blow dust and create dark streaks on the surface. Triton is a dynamic world, active despite its extreme cold, a moon that defies the expectation that distant, frozen worlds should be dead and unchanging. Mercury's day-night cycle is unique. Because of its 3-to-2 spin-orbit resonance, some locations on the surface experience double sunrises or double sunsets. As the sun rises, it climbs partway up the sky, then stops, reverses direction, and sets again before rising once more. This happens because Mercury's elliptical orbit causes its orbital speed to vary. At certain points in the orbit, the planet moves faster than it rotates, causing the sun to appear to move backward in the sky. The effect is subtle but real, a consequence of the interplay between Mercury's rotation and its orbit. It's one of the many peculiarities of a planet so close to the Sun, where the gravitational pull is strong enough to sculpt motion into patterns that seem almost impossible. Venus has highlands and lowlands, much like Earth has continents and ocean basins. The highlands, called tesserae, are rough, heavily fractured regions that rise above the surrounding plains. They're thought to be some of the oldest terrain on Venus, remnants of ancient crust that has been deformed by tectonic forces. The lowlands are smoother, covered by volcanic plains where lava flowed and solidified billions of years ago. Venus has no plate tectonics like Earth, so the crust doesn't recycle in the same way. Instead, the planet may undergo periodic resurfacing events, where widespread volcanic activity covers the surface with fresh lava. These events happen on timescales of hundreds of millions of years, erasing old craters and creating a surface that appears uniformly young. Venus's geology is different from Earth's, but it's not static. The planet reshapes itself, just more slowly and less predictably. Earth's continents are constantly moving, drifting at rates of a few inches per year. This movement is driven by plate tectonics, a process where the planet's outer shell is broken into large pieces that float on the semi-molten mantle below. The plates collide, separate, and slide past each other, creating mountains, earthquakes, and volcanic activity. Over millions of years, continents merge and split, forming supercontinents and then breaking apart again. The current continents were once part of a supercontinent called Pangaea, which existed about 300 million years ago. Pangaea broke apart, and the continents drifted to their current positions. In the future, they'll continue to move, and eventually they may come together again to form a new supercontinent. The process is slow, imperceptible in a human lifetime, but over geological timescales, Earth's surface is in constant motion. Mars has two large volcanic provinces, Tharsis and Elysium. Tharsis is the larger of the two, a raised plateau about the size of North America, covered in massive shield volcanoes. The largest, Olympus Mons, sits on the edge of Tharsis, but the region also contains three other volcanoes, Arsia Mons, Pavonis Mons, and Ascraeus Mons, all of them enormous. Tharsis is thought to have formed when a plume of hot material rose from deep within Mars, creating a region of intense volcanic activity. The volcanic eruptions lasted for billions of years, piling up lava in thick layers until the region was raised several miles above the surrounding terrain. Elysium is smaller and younger, but it also has large volcanoes and extensive lava flows. Both regions are now dormant, but they're evidence of a time when Mars was volcanically active, when magma flowed freely and reshaped the surface. Jupiter's atmosphere has been continuously observed for over 400 years, since Galileo first pointed his telescope at the planet. Over that time, the cloud bands have remained remarkably consistent, though individual storms come and go. The bands are created by wind currents that flow parallel to the equator, driven by the planet's rapid rotation and internal heat. The light-colored bands are called zones, where gas rises from below, cools, and forms clouds of ammonia ice. The dark bands are called belts, where gas sinks, warming as it descends and evaporating the clouds. The pattern repeats across the planet, alternating zones and belts, a structure maintained by the flow of heat and the spin of the planet. The consistency of the bands suggests that Jupiter's atmosphere is stable, locked into a pattern that has persisted for millennia. Saturn's rings cast shadows on the planet, but they also receive shadows. During Saturn's equinox, when the sun shines directly on the equator, the rings are edge-on to the sun, and the shadows they cast are razor-thin. But structures within the rings, like the embedded moons and density waves, cast their own shadows, creating a landscape of light and dark across the rings. These shadows reveal details that are otherwise invisible, showing where the rings are thick or thin, where material is clumped together, and where gaps exist. The equinox happens once every 15 years, and it's a time when astronomers study the rings intensely, capturing images and data that reveal the hidden structure of this beautiful, fragile system. Uranus has a relatively smooth appearance compared to Jupiter and Saturn. Its atmosphere lacks the prominent cloud bands and storms that characterize the larger gas giants. This is partly because Uranus is colder and its atmosphere is less active. The clouds that do form are faint and diffuse, hidden beneath a layer of methane haze. But occasionally, bright clouds appear, usually near the edges where sunlight strikes the atmosphere at an angle. These clouds are thought to be made of methane ice, condensing in the upper atmosphere and then evaporating as conditions change. Uranus's calmness is deceptive. Even though it appears featureless, the atmosphere is still dynamic, with winds and currents moving beneath the haze. It's just harder to see, hidden by the thick, uniform layer of blue-green haze that covers the planet. Neptune has a feature called the scooter, a bright white cloud that moves rapidly through the atmosphere. The scooter was observed by Voyager 2 and has been seen in Hubble images as well. It moves faster than the surrounding clouds, completing a full circuit of the planet in about 16 hours, while other features take days. The scooter is thought to be a plume of gas rising from deep within Neptune's atmosphere, pushed upward by convection, and then blown horizontally by winds. It's a transient feature, appearing and disappearing over time, but when it's visible, it's one of the brightest spots on the planet. The scooter is a reminder that Neptune's atmosphere is constantly changing, that clouds form and dissipate, and that the weather on distant planets is as dynamic as the weather on Earth. Mercury has a very eccentric orbit, meaning it's more elongated than most planets. At perihelion, its closest approach to the Sun, Mercury is about 29 million miles away. At aphelion, its farthest point, it's about 43 million miles away. This difference in distance affects how much sunlight the planet receives. At perihelion, Mercury receives more than twice as much solar energy as it does at aphelion. The temperature swings are extreme, with the day side heating up more intensely when the planet is close to the Sun. But the night side remains cold regardless, since there's no atmosphere to distribute the heat. Mercury's orbit is a study in extremes, shaped by the gravitational pull of the Sun and the lack of stabilizing influences like an atmosphere or a large moon. Venus's surface is hidden beneath its thick clouds, but radar has revealed a world of volcanic plains, highland plateaus, and impact craters. The surface is relatively young, about 500 million years old, which suggests that a global resurfacing event occurred at some point in Venus's history. This event may have been triggered by a massive release of heat from the planet's interior, causing widespread volcanic eruptions that covered the old surface with fresh lava. Since then, volcanic activity has slowed, and the surface has remained largely unchanged. The craters that exist are scattered randomly, indicating that they formed after the resurfacing event. Venus's surface is a snapshot of a planet in transition, caught between periods of intense activity and long intervals of calm. Earth's deepest point is the Mariana Trench, which reaches a depth of about 6.8 miles below sea level. The pressure at the bottom is over 1,000 times greater than at the surface, enough to crush most materials. But life exists even there, in the form of microbes and small invertebrates that have adapted to the extreme conditions. The trench was formed by the collision of tectonic plates, where one plate is subducted beneath another, creating a deep groove in the ocean floor. The trench is cold, dark, and isolated, but it's connected to the rest of the ocean through currents and the movement of water. It's a reminder that Earth's environment is not uniform, that extremes exist, and that life can find a way to survive, even in the harshest places. Mars has ancient riverbeds carved into its surface, evidence that liquid water once flowed across the planet. These riverbeds wind through valleys and empty into basins, forming networks that look remarkably like river systems on Earth. Some of the channels are small, only a few miles long, while others stretch for hundreds of miles. The channels are dry now, filled with dust and sand, but their shape and structure suggest that they were carved by flowing water. Mars's climate must have been very different in the past, warmer and wetter, with an atmosphere thick enough to support liquid water on the surface. That climate is gone now, eroded by the solar wind and lost to space. But the riverbeds remain, a permanent record of a time when Mars was more like Earth. Jupiter's moon Europa has relatively few impact craters, which suggests its surface is young, probably less than 100 million years old. This is remarkable for a moon that has existed for over 4 billion years. The lack of craters means the surface is constantly renewed, resurfaced by processes that erase old features. Ice from below rises to the surface, cracks open and refreezes, covering over craters and creating a fresh, smooth layer. Europa's surface is crisscrossed by long linear features called lineae, which are cracks filled with ice. These lineae form when the ice shell shifts and breaks, possibly driven by tidal forces or by the movement of the ocean beneath. Europa is a world in motion, constantly reshaping itself, hiding its history beneath layers of fresh ice. Saturn's moon Tethys has a massive crater called Odysseus, about 250 miles in diameter. The crater covers a significant portion of Tethys's surface, and it's so large that the impact that created it must have come close to shattering the moon entirely. But Tethys survived, and the crater slowly relaxed over time, flattening as the ice beneath it flowed like a very slow liquid. The result is a crater that's shallow relative to its width, with a floor that's nearly level with the surrounding terrain. Tethys also has a long canyon called Ithaca Chasma, which stretches about 1,200 miles across the surface. The canyon may have formed when Tethys's interior froze and expanded, cracking the surface. Tethys is a world marked by violence, but it's also a world that healed, smoothing over its scars through the slow movement of ice. Uranus's moon Titania has canyons that cut across its surface, some of them hundreds of miles long. These canyons are evidence of tectonic activity, possibly caused by the expansion of Titania's interior as it froze. Water ice expands when it freezes, and if Titania's interior was once liquid and then solidified, the expansion would have cracked the surface, creating the canyons we see today. The canyons are relatively young, with fewer craters than the surrounding terrain, which suggests they formed after most of the heavy bombardment of the early solar system. Titania's surface is a mix of old and new, ancient plains covered in craters, alongside younger features that tell the story of a moon that changed over time. Neptune has 14 known moons, and more may be discovered as observations improve. The moons vary widely in size, shape, and orbit. Triton dominates the system, accounting for more than 99% of the mass of all of Neptune's moons combined. The other moons are small, irregularly shaped, and many of them orbit in highly inclined or eccentric paths. Some of the small moons orbit within Neptune's rings, acting as shepherds that keep the ring arcs confined. Others orbit far from the planet, possibly captured objects from the Kuiper belt. Neptune's moon system is diverse, a collection of objects with different origins and histories, brought together by the gravity of a distant planet. Mercury's surface temperature varies more than any other planet. The day side, facing the sun, can reach 800 degrees Fahrenheit, hot enough to melt some metals. The night side, turned away from the sun, drops to nearly 300 degrees below zero, colder than the surface of Pluto at times. This extreme swing is caused by Mercury's lack of atmosphere, which means there's nothing to trap heat or distribute it around the planet. The temperature changes gradually as the planet rotates, taking 59 Earth days to complete a single turn. If you stood on the surface and watched the sun move across the sky, you would feel the temperature rise degree by degree, reaching its peak at local noon, and then falling again as the sun set. The cycle is slow and steady, a rhythm dictated by the planet's rotation and its proximity to the sun. Venus's clouds are made of sulfuric acid droplets, which form when sulfur dioxide and water vapor combine in the upper atmosphere. The droplets are tiny, only a few micrometers across, and they scatter sunlight efficiently, which is why Venus appears so bright. The clouds are layered, with the thickest layer sitting about 30 to 40 miles above the surface. Above and below this layer, the air is clearer, but the clouds themselves are opaque, blocking any view of the surface from space. The acid rain that falls from the clouds never reaches the ground. It evaporates in the hot, dense atmosphere long before it gets there, turning back into gas and rising to form clouds again. Venus's clouds are a permanent feature, part of a cycle that has continued for millions of years. Earth's atmosphere glows faintly at night, a phenomenon called airglow. It's caused by chemical reactions in the upper atmosphere, where oxygen molecules excited by sunlight during the day release energy as they return to their normal state. The glow is too faint to see with the naked eye in most places, but it's visible from space and can be photographed from the International Space Station. Airglow is not the same as the auroras, which are caused by charged particles from the solar wind colliding with the atmosphere near the poles. Airglow happens everywhere, all the time, a gentle luminescence that wraps the planet in a soft light. It's a reminder that the atmosphere is not just a layer of gas, but a dynamic, reactive system, constantly responding to the energy from the sun. Mars's atmosphere glows faintly in ultraviolet light, a phenomenon detected by spacecraft orbiting the planet. The glow is caused by the same type of chemical reactions that create airglow on Earth. But on Mars, the glow is driven by the thin atmosphere's interaction with solar radiation. The glow is strongest on the day side, where the sun is shining, but it also occurs on the night side, powered by chemical reactions that continue even in darkness. The glow is too faint to see with the human eye, but it's measurable with instruments, a sign that Mars's atmosphere, though thin, is still active and responsive. Mars may seem quiet and still, but even in its silence, processes continue, energy flows, and the atmosphere glows softly in the dark. So, wherever you are, allow your mind to rest. Let your breath slow. Let your thoughts grow soft at the edges. The planets continue their orbits, turning through space in patterns older than memory, indifferent to time and untouched by haste. They've been moving this way for billions of years, and they'll continue long after we're gone. There's comfort in that kind of permanence, in knowing that some things remain steady while everything else changes. The universe doesn't rush. It simply unfolds, one rotation, one orbit, one quiet moment at a time. The journey doesn't end here. It simply pauses until curiosity calls again, until the next time you look up at the night sky and wonder what's out there, waiting in the darkness. Sleep well, and thank you for drifting through the cosmos with us tonight.